All right, so our next hypothesis test is going to be the hypothesis test for the population mean. So before we start, I'm going to go through the basics. The test itself is, in the broad sense, no different than any other hypothesis test we've done to date. All right, there's some conditions that we have to have met, and these are right here. All right, the sample has to be a simple random sample from a randomized experiment, or from a randomized experiment. The sample has to have no outliers, and the population from which the sample is drawn is normally distributed, or the sample size is large, and we're considering greater than or equal to 30 as being large. The sample values have to be independent from each other. That means the sample can't be too large with regard to the population. All right, as long as those conditions are met, then our test statistic variable should follow the student t distribution, and we'll be able to do the hypothesis test. So our steps basically the same, right? We determine the null and alternative hypothesis, all right, one of those three possibilities. Select the level of significance depending on the seriousness of making a type 1 error. Now again, for the problems you're going to see, you'll be given alpha, but if you're doing this out in the real world, then you'll have to figure that out. We're going to compute a test statistic. Now, for us, the test statistic is the t-value, again, using the sampling distribution formulas. We get our cutoff value from the table in the book, which I will show you, the student t-distribution table, and then you decide where your value falls, okay? And then you state your conclusion. So in the broad sense, it's the same basic pattern as we've had for every other hypothesis test. All right, so let's just jump straight into it and go straight to a problem. All right, this one says the mean height of American males is 69.5 inches. The heights of the 43 male U.S. presidents, Washington through Obama, this book was published a little while ago, have a mean of 70.78 inches and a standard deviation of 2.77 inches. Treating the 43 U.S. presidents as a simple random sample, determine if there's evidence to suggest that the U.S. presidents are taller than the average American male, and use an alpha of 0.05. All right, so there's a few things we need to do here. I'm going to go through the classical method first, and then once we have the classical method done, I'll show you the p-value method. All right, so as usual, the first thing I want to do is pull some information out of the problem. All right, so the first thing we need is the population mean, and the population mean is given in the first sentence, right? That is the mean height of American males, which is 69.5. We need our sample size, so the sample is 43 U.S. American presidents. Our sample mean, the mean height of the U.S. presidents, is 70.78. And the standard deviation of that sample is 2.77. All right, so all that information is given to you in the problem. All right, sample size, mean, sample mean, and sample standard deviation. All right, the other thing I need is my alpha value. So alpha is 0.05. All right, so there's all my information. I can set up the hypotheses. So the null hypothesis, remember, null hypothesis, statement of no change. The population mean is what we say it is, 69.5. The alternative hypothesis is the claim that we are trying to find evidence for. All right, so if we go back to the problem and look at the question, determine if there's evidence to suggest that U.S. presidents are taller than the average American male. All right, so taller would be greater than 69.5. All right, so when I set up my normal curve here, I'm looking at a right tail test, because greater than is right. So I need the critical value here. So a right tail test means we're using alpha. All of alpha sits over here, so we're using alpha. All right, so alpha is 0.05, and then I need my degrees of freedom, right, which is n minus 1. So my degrees of freedom are going to be 42. So we need to take a look at the student t distribution. All right, so here is the student t distribution, and alpha equals 0.05 is right here. And if I scroll down my degrees of freedom, notice that at 40, there is no 42. It jumps right from 40 to 50. So you're just going to go with whichever one of those is closer. All right, so 42 is closer to 40 than to 50, so 40 is what I'm going to use. So let me go back up here for a minute. All right, so here is the alpha equals 0.05 column. So if I follow that column down, I get right here 1.684. Okay, so 1.684 is going to be my cutoff. So 1.684. Okay, I can calculate my test statistic. So z is going to be x bar minus mu, so 70.78 minus 69.5 divided by, and then our adjusted standard deviation. So that is going to be the standard deviation, 2.77, divided by the square root of n, and n is 43. All right, now I've said before, you want to do this whole thing on the calculator in one step. This way you avoid any kind of round off errors. So remember to put the numerator and denominator separately inside parentheses. So paren 70.78 minus 69.5, close the parenthesis for the numerator, divided by, open a paren for the denominator, 2.77 divided by the square root of 43, close the square root, close the denominator, and there we go. All right, so remember with the t-scores, we want to round these to 3 decimal places. So 3.0301 is going to round to 3.030. Right, so if we come over here, we say 3.030. And my cutoff, right, my critical value is 1.684. So 3 is going to fall way out here somewhere, right? 3.030. All right, so remember when we're looking at the diagram, the shaded area is the critical region. The unshaded region is the do not reject. Forgot to fill that in. All right, so we land in the critical region, so that means we get to say reject 80. All right, essentially our evidence, our sample, is unusual under the assumption that the null hypothesis is true. All right, so that means we have to reject the null hypothesis, which means there is enough evidence to suggest that the height of 43, the average height of the 43 U.S. presidents is taller than the average American male. All right, so you just want to state that as your conclusion there. So I'm going to do this quickly. is enough evidence to, I'm just going to say to support the claim. I would also go on to claim. I would also go on to state the claim at that point. There is enough evidence to support the claim that the height of the U.S. presidents is taller than or higher than the average American male. All right, so doing the problem using the classical method. All right, again, the only difference between what we did in the others is just, it's always, the difference is always in how you calculate the test statistic. Now, if I want to do this using the p-value, all right, I'm going to go to my calculator, and I'm going to go into stat, and I'm going to go to tests, and notice the second test in the list here is t-test. All right, so t-test is what we're doing. Now, when you pull up the t-test, there are two choices for how you do the test. You could do it with data, or you could do it with statistics. We don't have data, right? We don't have the actual heights of all of those 43 U.S. presidents. All right, so what we have is statistics. They give us the mean and the standard deviation. So the first thing I'm going to do is go over to stats and highlight that. And now what it's asking me for is the sample mean and the sample standard deviation and the sample size. All right, so we're going to come down here. Now, mu0 is always your population mean. So 69.5. All right, the sample mean is 70.78. The sample standard deviation is 2.77. My sample size is 43. And then I just have to choose which test I'm doing. All right, so we are doing, again, that's determined by the alternative hypothesis. Mu is greater than 69.5. All right, so, all right, we are talking about greater than as our test. Okay, I think we're ready to go. Down here, calculate. All right, so let's take a look at what we got. They gave us our alternative hypothesis, so that matches, right? They gave us the t-value that we just calculated, right? I said z here, I meant t. All right, the t-value that we just calculated here. And they give us our p-value. And then they repeat some of the information that we put in. So the p-value, right, the p-value to 3 decimal places is 0.002. Our alpha value is 0.05. So remember what the p-value tells us, right? The p-value is the probability that based on our sample data, we've made a type 1 error, right? Our maximum possible type 1 error that we're allowing for is 0.05. All right, my data is showing a lower probability of making a type 1 error. So my p-value is less than my alpha value, which again is our criteria for being able to reject the null hypothesis. All right, it's saying there is less of a probability that we're going to make a type 1 error using our sample data than we're allowing for. So that's a good thing. Okay, that means our data is unusual under the assumption that the null hypothesis is true. Okay. All right, so you can use your calculator to get the p-value that way. Now, there's a couple of other things to think about when we are doing hypothesis tests for the mean. And those involve the types of sample that we're looking at. So, what happens if we don't have everything we need up here in these conditions, right? Let me come back down, come back up here. All right, so remember our conditions, two of our conditions involved All right, well, first of all, the sample has to have no outliers, and the population from which the sample is drawn is normally distributed, or the sample size is large. So what if we don't have some of those conditions met? What happens if we have a small sample, all right, and in addition to the small sample, all right, we don't know anything about the population? All right, so we've talked about these hypothesis tests in terms of quality control in the past. All right, so let's look at this example here. The fun size of Snicker bar is supposed to weigh 20 grams. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so that the weight is 20.1 grams. The quality control engineer at M&M Mars, the Snickers manufacturer, is concerned about the calibration. He obtains a random sample of 11 candy bars and weighs them, and obtains the sample shown in table right here, table 1. So we've got 11 weights of our candy bars here. Should the machine be shut down and recalibrated? Because shutting down the plant is very expensive, he decides to conduct the test at an alpha equals 0.01 level of significance. All right, so notice a couple of things here with this data. The first, it's a small sample, right? It is definitely less than 30. There are only 11 candy bars sampled. The other thing is they don't say anything about the population of the weights of these candy bars being normally distributed. Now, they may be, they may not be, but that's not being indicated here. So it may be a situation where they don't know. All right, so since we don't have two of those conditions met, we don't know that we have a normal probability, and we don't know, we don't have a small sample. We have to do some checks. All right, and the checks we're going to do are checks that we've talked about before in class. And that has to do with doing a normal probability plot and taking a look at a box plot. All right, now the other thing that you would want to do is to do a normal probability correlation test. Now again, we didn't cover that. That's not required for our class. There is a video up on the YouTube channel about how to perform that test. I'm not going to go into too much detail because you can just watch that video. It's the normal probability, testing normality using Excel. All right. As far as you guys are concerned, in this class in particular, you will be given this information and you will have to examine the information and make a determination as to whether or not you can proceed. All right. So what you'll be given is a normal probability plot and a box plot. Now, before I get into the other information, when we look at the normal probability plot, it doesn't really look super linear here. It is, but the trend is upward and to the left. So there's a general increasing trend, strictly increasing trend here. All right, there's no place where it drops down and takes a really strong wiggle. All right, let's say. So we do have a strictly increasing trend, which is one of the things that we want to look for in the normal probability plot to indicate approximately normal. Now, when we look at the box plot, you can see the box plot definitely has a right skew to it, but you'll also notice there's no outliers, okay? There are no points that are outside the maximum or minimum values. All right, so one of the conditions was that the sample data has no outliers. So we have no outliers in this data, so that's a good sign, even though this does look a little bit of a right skew. So then you would do, or you would be given, the normal probability correlation test, all right, which is coming up as 0.967, which is a positive linear correlation. Whether or not it's significant is going to depend on the critical value for a sample size of 11. And in your book, that is table 6. All right. Otherwise, you would just look for a table online for normal probability correlation coefficient test critical values. I think that would be enough. All right, and you'll find that the critical value there is 0.923. So our correlation is higher than the critical value, which means I can say that this correlation is significant. So what all of this allows me to conclude, all right, is that we can proceed with the hypothesis test. All right, we're dealing with a sample that is approximately normal. And that is the alternative to having a population that is normal. Okay, so our sample is approximately normal. We can then move forward with the test. All right, so if you want to see the rest, just to see how it works out, the rest of the test, right? The engineer wishes to determine whether Snicker bars have a mean weight of 20.1 grams or not. Okay, so that is a two-tailed test, right? My null hypothesis and alternative hypothesis. Here is the level of significance. So if we want to do this as a p-value test on the calculator, right, you would input your sample data into L1, and then when you go to your t-test, you're going to select data rather than stats, all right? And you'll be able to complete the test that way, okay? All right, so if I move on here real quick. All right, so from the classical approach, if we proceed with the classical approach, I'm going to do my t-score and get 1.042, okay? And I'm going to go to my student t-distribution table and find out that the critical value or cutoff here is 3.169. All right, so because my t-value falls in between those two, not in the critical region, we are not going to reject H0. All right, this result is not unusual under the assumption that the null hypothesis is true. All right, so we don't get to reject the null hypothesis in this case. If you go for your p-value, all right, the calculator, or this textbook is using Minitab, the calculator is going to come up with a p-value of 0.323. Remember, our alpha value is 0.05. So in this case, the p-value is greater than the alpha value. That means that the probability of making a type 1 error is higher than we're allowing for based on our data. So that is our criteria for not rejecting the null hypothesis. All right, either way, all right, there is not sufficient evidence to conclude that the Snickers have a mean weight different from 20.1 grams. All right, at the alpha equals 0.01 level of significance, so the machine should not be shut down. All right, so when you're working with a small sample, right, when you're working with a small sample, just remember you're going to see basically all of the information from this sentence here, the correlation between the weights and expected z-score is, and the bottom down here with the two weights, and you'll need to make a decision for the online homework or, you know, for the exam or something like that, for the online exam. You would need to make a decision. Or, again, if you were out there doing clinical research or quality control research, you would need to perform these tests to make sure that you could actually do the test that you want to do. All right. All right, so there's one other little tag here that I want to throw in. All of this involves tests that are giving us what's called statistically significant results. All right, so it is statistically significant that the candy bar weights are not different. All right, but there is a difference between statistical significance and practical significance. All right, yes, this is statistically true, but is it practical? All right, so let's take a look. I'm going to take a look at this example right here as our last example. So according to the American Community Survey, the mean travel time to work in Collins County, Texas in 2013 was 27.5 minutes. The Department of Transportation reprogrammed all of the traffic lights in Collins County in an attempt to reduce travel time to determine if there is evidence that travel time has decreased as a result of the reprogramming. So the Department of Transportation obtains a random sample of 2,500 commuters, a large sample, records their travel time to work, and finds that the sample mean is 27.2 minutes with a standard deviation of 8.5 minutes. Does this result suggest that travel time has decreased at the alpha equals 0.05 level of significance? All right, so we go through and we perform the hypothesis test. I'm not going to do it. I'm just going to show it to you. Okay. All right, so we set up the hypotheses, right? The mean travel time is 27.5. That's the assumption. All right, we were trying to see if the travel time is decreased. So H1 is that the mean travel time is less than 27.5. We calculate the test statistic and end up with negative 1.765. And I'm going to talk about the classical approach here. Okay, well, actually, let's just talk about the p-value. So the p-value, if we calculate the p-value based on this information, the p-value ends up being 0.03. And remember, our alpha value up here is 0.05. That means our p-value is less than the alpha value. All right, so if the p-value is less than the alpha value, we get to reject the null hypothesis. The probability of making a type 1 error based on our sample data is less than what we're allowing for. All right, so we get to reject the null hypothesis, which means there is sufficient evidence to conclude at the 0.05 level of significance that the mean travel time to work has decreased. All right, so at this point, the Department of Transportation is probably going to start an ad campaign saying, you know, we spent this money to reduce travel time to work. We performed our tests and we have concluded that there is a statistically significant result that travel time has reduced. All right, here's the thing though. All right, the difference in the travel time, 27.2 and 27.5, is 0.3 of a minute. 0.3 of a minute is 18 seconds. So yes, travel time is reduced. Yes, the results are statistically significant, but is 18 seconds really going to make a difference for anybody? Okay. This is the kind of thing that you see a lot in marketing. All right. They'll change a product, right? And say this product is better because, but without giving any specific information, because they've done a test, they've come up with statistically significant results. Those results are minuscule, but they're statistically significant, so they are allowed to say this is better or this is different. All right, when the reality is it's really not. So always take when you do a hypothesis test, and this is for any hypothesis test, don't just take the results and run with it, all right? You always want to take your results and examine them. Okay, yes, this is statistically significant, but is there a practical significance to the difference? All right? Okay, so that will finish off our current hypothesis test set, and I will get this video posted.